Hi everyone, this is Twitter Think and I will be talking about linear first order differential equation in this video. How to solve a linear differential equation or an ordinary differential equation using what we call the integrating factor. So any differential equation of the form dy dx plus py equal to q is an ordinary differential equation or a linear differential equation. The equation can also be in the form dy dx m of x y equal to L of x. Remember that m of x, L of x, or p and q are two separate functions in terms of the variable x. That was why I gave this example so that you know the difference. So p and q, or m and l, are two separate functions in terms of the variable x only. And this is called a linear differential equation since the variable y and its differential dy dx are of the first degree. So this is what we call a linear first order differential. But this equation, either this or this, can be solved by multiplying the function or the whole equation through by what we call the integrating factor. Now I will talk about the integrating factor. Now the integrating factor is equal to e to integral of p dx. Remember that I'm using p here because I want to work with what? P and q, not m and l. Now p is the function, the first function here, that is multiplying what? Y, p ds. Let's assume that the integrating factor is equal to capital R. I want to use capital R to make it very simpler for us to understand. Now the integrating factor is usually a function that is used to solve differential equations, and it is used to multiply an ordinary differential equation, like I said earlier, to make the function integrable. So to be able to make the function integrable, meaning that it will be easy for us to integrate that function if we multiply through by the integrating factor, this, or assuming it's this one. So now this is an introduction video. Once we take a typical example, you will understand what I am talking about. So now let's move on. Now after we multiply the integrating factor by the equation, what is next? So let's see what will happen. So now when we multiply the equation through by the integrating factor r, this is what we are generating: r times dy dx plus rpy equal to rq. Let's label this one equation 1, like I said here. Now what this means is that the solution for the linear differential function can only be obtained if we multiply through by the integration factor, and that is what I have done. Now after we do this multiplication, the next thing to do is to find what we call the differential coefficient of ry. What this means is that when we move to the left hand side of the equation, we need to take the derivative of the integrating factor and the variable y. So the r and y are two products, and to be able to do that, we need to apply what we call product rule in differentiation. Most of you are aware of that, so let's see what will happen. So the differential coefficient of ry will be obtained using the product rule. So most of us are aware of product rule. So to use the product rule, what we are saying is that we are taking the derivative of what? R and y. P is a function in terms of the variable x. We are not yet interested in that. So derivative of ry in terms of the variable x will give us, from product rule, most of us know that hold the first variable, differentiate the second, come back and hold the second variable, differentiate the first, and sum it up. So now we have, let's hold r, differentiate the second variable, which is derivative of y, the same as dy dx, plus hold the second variable, which is y, differentiate the first variable, which is what? R. So dr dx. Now from product rule, this is what we are getting. Now listen very carefully. Whatever that we have here is the differential coefficient of what? Ry. Now the differential coefficient of Ry will only be equal to the left hand side of equation 1 when we assume that Rp is equal to what? dr dx. Let me write that and then explain. Now, like I said earlier, listen very carefully. Linear first order differential equation is saying that the only way the left hand side of equation 1, which is this side, the left hand side of equation 1 will be equal to the differential coefficient is when we assume that Rp is equal to what? dr dx. You and I, we have to take it like that. Now, when we choose R such that Rp, remember that P here is a function on its own in terms of the variable x. We will come across that in our examples. Now, when we assume that Rp is equal to dr dx, then we can vividly say that the left-hand side of equation 1 is equal to this. Now, watch very carefully. If I replace Rp with dy dx, this is what I am getting. So I'm having r dy dx plus, now the rule is saying that choose Rp to be what? dr dx. So we have our dr dx times y equal to what? R cubed. This is equation 1 star. Now watch very carefully. Everything that we have here now is equal to what? The differential coefficient of what? Ry. And we can see they are the same. If I bring my r here, they are the same. So that is how we tackle linear first order differential equation using the integrating factor. Now when we consider Rp, which is Rp to be equal to dr dx, then it will be possible for us to separate variables to generate what we are looking for. What am I looking for? The integrating factor. And using the integrating factor, we can integrate the main function that is given to us. So now that you have gotten the concept, if we say that Rp equals dr dx, then we need not to worry because whatever function we have here, the coefficient function, differential coefficient function, will be equal to the left hand side of the equation, and we are not interested in that. So we are only interested in the result Rp equal to what? dr dx. Now we can separate variables, and let's see what will happen. This is when separation of variables means we are grouping the function in terms of the variable x and in terms of the variable r. Remember r here, I'm using r to represent the integrating factor. To help some of us to really understand, I will separate variables by showing work. And to do this, I know this is over 1. I can just cross multiply here. And this is going to give me Rp times dx equals dr. Now, because I want to separate variables, I will divide through by what? R. Now, this is over R. This is over R. I can take care of this one, and I am having P dx equals dr over R. Now, P here is a function, and remember that in the beginning, I told you that P is a function in terms of the variable x. I am using P. Now, let's come back here. And I told you that I can also use something like M in terms of the variable what? X. So here we are having P in terms of the variable x. So if I separate variable, I have to separate variable such that the x will be attached to what? P. Now, do you get the concept? Since we are assuming that there is the function P is in terms of the variable x, so I separated them together. Then I separated the R and R together. Now, so this is the same as dr out of R equal to P dx. Now we can apply integration at both sides. We integrate this side and we integrate this side. Now let's move on. So when we apply integration at both sides, what are we getting now? I can rewrite this as the integral of 1 over r dr equal to the integral of p dx. Now from basic integration, 1 over r, or the integral of 1 over r, is the same as ln r. So now we have ln r equals, now I do not have the function p of x or the function p in terms of the variable x. So I will repeat that side and bring my constant of integration. So this is the integral of p dx plus c. Now in our next step, we would want to get rid of the natural log ln, and to do that we need to introduce the exponential function e. So this is the same as me having e raised to power ln r equal to e raised to power integral of p dx plus c. Now this will now take care of this, and we will be left with what? R. So we have r equals e to power integral of p dx plus c. Now from logarithm or indices, the right hand side, is it logarithm or indices? Let's move on. From that, we can rewrite the right hand side in the form r equals e exponent integral of p dx times e exponent c. When I multiply this, I can take one base and add the powers, and I'll get back that. Don't know if this is indices or anyways. So now let's assume that e raised to the power c is a constant. So let's use a variable. Let's say a. So we can say that let e to power c be equal to a, and the equation becomes r equals e exponent p dx times a, and this is the same as r equals a e p dx. Now let's label this one equation 2. Now we are going to substitute equation 2 back into what? Equation 1. Now substituting 2 into equation 1, what do we have? Let's go back to equation 1. This is equation 1, and in equation 1 we have r dy dx plus r p y equal to rq, and that is equation 1. So let me put it down. So wherever we see r, we are substituting equation 2. So let's do that. So this is giving us a e to p dx dy dx plus a e integral of p dx times py, let me put my multiplication dot here, equal to a e integral p dx times q. Now look at this very carefully. Let's put this in one bracket. We can divide through by a to get rid of a. So let's assume we have done that, and the equation now becomes e integral p dx times dy dx plus e integral p dx times py equal to e integral p dx times q. Let's label this equation 3. Now look at equation 3 very carefully. You can see that by the end of the day we have been able to use r to generate the integrating factor, which is e integral of what? P dx, and we have substituted this here. This equation 3, it is the same as equation 1. When you look at this, r. and now we have this is the same as r, this is the same as r, this is the same as what? R. And also in the beginning I was saying that the differential coefficients of Ry is what is very important to us, because when we take the differential coefficients of Ry, the result is equal to the left hand side of what? Equation 1. So that is what we have here. The left hand side of equation 3 is derivative of y and this, which is the integrating factor, which may be checked by differentiating y times the integrating factor with respect to x using product rule. Now this means that when we take the derivative of e and y, we will generate this side of the what equation, especially this. So it is very important that anytime you are solving a linear differential equation, when you get here, there is no need to solve this side. All you need to do is to take the derivative of what? The variable y and the integrating factor and equate it to what? The right hand side of the equation. Now let's see what this statement means. Now assuming that I have the function y times what? The integrating factor, forgetting the function p with respect to x. Now watch carefully. When I differentiate this with product rule, I will hold the first variable or the second. So let me hold e p dx, then I'll multiply by the derivative of y, giving me dy dx, plus I'll hold y, then I'll differentiate this side, derivative of what? P dx in terms of dx. Now watch this carefully. We can see that the result of the derivative of this is generating the same function. Now this side is the same as whatever that we have here. So we say that it is the same as the left hand side of the equation if we take the derivative of the integrating factor and the variable y and equate it to what? The right hand side of the equation. So let's see what will happen. So in our next step, we are just supposed to take the derivative of e and y equal to what? The right hand side of the equation. Now this result is going to be written as this. So derivative of the integral function of the integrating factor and y should be equal to this. Our next step is to what? Integrate both sides. So integrating both sides, what are we getting? So therefore, the integration side will now take care of this derivative function. And we are having ye integral of p dx equals integral of e integral p dx times q. So therefore, our integrating factor here is e integral p dx. Don't forget this e is an exponential function. And this is the end of linear first order differential. So linear first order differential equation is just saying that after you generate equation 3, where you multiply each side of the equation by the integrating factor, this is the derivative term, multiply by the integrating factor, multiply the function py by the integrating factor, and multiply the last function q by the integrating factor. From there, take the derivative of the variable y and the integrating factor on the left hand side. So that is what we have here, and equate it to the right side of the equation. And that is what I have here. By doing so, the derivative of this function will still generate the left hand side of equation 3. And when that happens, apply integration at both sides, get rid of the derivative function, and integrate the right hand side of your equation to finish your calculation. So this is how we solve first linear order differential equation. In my next video, I'll be taking examples of these same functions and how to prove them. And from there, I'll take examples under the main question and then solve. I'll take 2 or 3 examples for you to understand whatever introduction we spoke of today. So my name is Daniel. I hope this was very helpful. Kindly subscribe to this channel and stay tuned. See you in the next one.